So let's talk a little bit about rockets, orbits, and the space environment. I think last week we talked about how space affects design. So how you have to consider the differences in space compared to on the Earth. Can someone tell me what those differences were? Yep.
Lack of gravity.
Lack of gravity. Okay, so what impact does that have?
Their muscles aren't used to not having to do as much work.
Yep, okay, definitely. So that's for humans. It also has some impacts on robots as well. Some fuel systems and that sort of thing get impacted by it.
Lack of air pressure.
Yeah, right, absolutely. So space is a vacuum, there's no air pressure. It affects all kinds of fluid motions, it affects a lot of things in space, especially people. Anything else?
Temperature and radiation.
Temperature and radiation, yeah, that's two. So temperature, definitely it's very cold, but it's more that the heat transfer mechanisms are very different. In space you have just radiation, heat transfer. You also have conduction through materials, but you don't really have that convection. So on Earth, we lose most of our heat by it actually getting just picked up by the air. And in space, you don't have that at all. So it makes hot things get really, really hot because they don't dissipate energy very well. And it makes cold things stay very cold. Radiation, you mentioned as well, so that affects humans obviously, and it also affects computer systems. It causes a lot of bit error rates in data. It's kind of like a Geiger counter. You can actually detect bits of radiation coming through the surface, and they're little mini particles that you can't even see, and they hit circuits and cause electrons to move or cause spikes in voltage, which throws off all kinds of computer systems and damages memory. How do we move around in space? You can't use a propeller, for example. You can't use a car engine and wheels. So how do we move around in space?
A
Rocket. So how does a rocket work? Yeah, combustion. Okay, but there's a specific law. Anyone tell me what that law is?
Whenever there's a force, there's obviously equal and opposite.
Absolutely right. That's Newton's third law: equal and opposite reaction to any action. So if you push something out, so push some mass out, depending on the mass and the velocity, that creates momentum, and you have a force in the opposite direction to that. So basically all we do is throw stuff out the back. You actually move around in space just by throwing tennis balls, for example, and every tennis ball you throw gives you a push because it's conservation of momentum. That's what it's actually based on. So if I have a certain momentum and I throw something that way, then the total momentum of the system has to be conserved, which means whatever momentum I've imparted to that tennis ball, that momentum gets subtracted from me. In fact, it ends up, because if it's negative, it ends up in the opposite direction, so I get pushed by that. Absolutely right. So because there's no air pressure, it means you can't push against anything. So that's why we have to rely on Newton's third law to move around in space. So that's what a rocket does. It just throws things out the back. And the ability of a rocket to move you depends on the amount of stuff it can throw out and the speed at which it throws it out. So there's two factors there, and they have really big impacts and implications for rocket design and space missions. Now, what about orbits in general? Why do we use orbits in space, or why do they result in space? Anyone know anything about orbits? Want to guess? Why don't we just go in straight lines?
Because of gravity and inertia. Well, inertia is in straight lines, but gravity makes it go straight.
Yeah, that's absolutely right. So if we're here on the Earth and we shoot a cannon or something, the cannonball will fall, and it'll follow this parabolic trajectory, and it'll always fall. And then all in orbit is a cannonball that shot so fast that it's still falling, but every time it falls, it's also avoiding the Earth. So it's always falling towards the center at every point, but it can never get there because it's also moving so fast tangentially, horizontally, that it never actually manages to fall to the surface. So it's kind of trying to fall to the surface. And because Earth has this atmosphere that's about 50 kilometers thick, if you're above that atmosphere, you can actually do this with no drag and just stay up there forever. So one thing about orbits is there is air, and it's not complete margin between lots of air and then no air. It's actually a very gradual decline. So the number of particles can be plotted as hyperbolic trajectory. So when you are close to the Earth, I guess this is at the Earth's surface, this is space, and eventually it does get to pretty much zero, but it falls off the number of particles. So you actually do get drag in orbits if you're close to the Earth. The space station gets quite a lot of drag in orbit, and they have to do station keeping. They have to burn some rockets to actually keep it up in orbit. Otherwise, it would fall down, like on a yearly basis. So it's a very little amount of drag, but it still gets drag in orbit. Is there anything else you could do in space other than use a rocket?
Solar sails.
Yeah, solar sails. So you can get anything else. Basically, you want to be pushed, and the sun does emit a pressure, and you can actually take that if you have a really big sail. Yeah, so that's actually a type of rocket. Ion engine is a type of rocket, but there's a big difference there. With a chemical rocket, your objective is to push out as much as possible very, very fast. But with an ion engine, you push out just a little tiny bit extremely fast. And so you get a really good efficiency from that because you're not burning very much propellant, but you're pushing it out very, very fast. So what types of spacecraft are there? Yeah. Probes, yeah. Satellites, yeah.
So chemical propulsion versus like electrical propulsion?
Yeah, so those are two different types of engines and rockets, yeah. But basically a spacecraft is anything we put in space. It's an enclosed space. Even a space station is a spacecraft, like the International Space Station is a spacecraft. Curiosity, even though it's on a planet in an atmosphere, Mars's atmosphere, is still a spacecraft. Apollo capsule over there, that's a spacecraft as well. That's Mir Space Station. Okay, so here's some examples of launch vehicles. The one on the left here, that's an Indian one. It's called PSLV, Polar Satellite Launch Vehicle. This is SpaceX. This is Falcon 9, which is one of the best commercial launchers today. It's just coming out now. They had their third flight to the International Space Station last week, actually. This is Ariane 5. It's the most popular European launcher. And this is a Chinese launcher. This is the one they launched their humans on. Actually, Changjiang Long March. It's called Long March 5. So this is the mathematical basis of a rocket. The change in velocity that you get, so how fast you start at compared to how fast you end up at, is equal to the exhaust velocity, VE. So that's the velocity at which the propellant comes out the back of the rocket, times ln, so natural logarithm. Do people know what a ln is, natural logarithm? Some people, you know what logarithms are, but it's to base e. It turns out to be this really interesting mathematical value. And this is the initial mass, and that's the final mass. So how fast you go depends a lot on your mass. So it's actually a logarithm of mass, so it's highly nonlinear. And another really important thing is your exhaust velocity. So the faster you can get stuff coming out of the back of the rocket, the much better it is for efficiency. Because both of these masses, in those masses is included your fuel. In your initial mass, your fuel is included in that. So your objective really is to burn the least amount of fuel. Basically, the efficiency of a rocket is determined by how fast the gases come out. So the faster you can put something out the back of the rocket, the more efficient it is because you can get a bigger change of velocity. So you want to get it coming out as fast as possible. Now, the power of a rocket, the thrust of a rocket, is determined by the amount of stuff you can push out. Doesn't really matter how fast it is, but it's how much can you push out because you get a much larger force. And so this means that there's this really interesting trade-off between pushing propellant out as fast as possible versus pushing as much propellant out as possible. And if you push out propellant faster, you have more efficiency and less propellant used. But if you push out more, you have more thrust and you actually have more pushing power. So if you solve this, how much propellant is needed to get a 50 kilogram person to escape velocity, so away from the Earth, with a solid rocket? And this is a typical exhaust velocity, and it turns out that it's over 10 times as much. And that's just for one person. Can anyone make any observations? This means that rockets are very inefficient. The way rockets are designed is they're basically giant fuel tanks with some small payload aboard. So your actual payload, the actual thing you can carry to space, like the person in this case, and this is of course without any protective shell, they would need a lot more than that. This is if you're just sitting on a lawn chair. But you would need a lot more stuff, and so you need 10 times as much fuel as the stuff you're sending. So that's a typical ratio for a rocket. In fact, it's usually worse than that. That's the best theoretical ratio is the amount of stuff, the amount of payload you can send into space is about equivalent to 1/10 of the weight of the rocket. That's about the theoretical maximum limit. And it's usually much, much worse than that. It's usually on the order of 1%. Have you guys ever seen the Apollo stack? So you have like the moon rocket. It's got the people at the top in this little capsule, like that, which is maybe, I don't know, 15 feet across or something like that. And then they're on top of this stage here, and then this stage here, and then this stage here. And the whole thing is like 500 feet tall or something, and they're just this little tiny thing. It's because the weight of this is about 1% of the entire weight. And almost all of this is just fuel. And what else is interesting about this? There's actually 3 parts, right? Why would you do that?
One for getting out of the atmosphere, and then one for maybe like getting closer to the moon, and then one for minor adjustments.
Yeah, well, yeah, sort of. Actually, the main reason is because you want to reduce the mass as far as possible. So you want to use this to fire as much as possible. You don't even use this, but you use this up, and then you shed the dead weight, because now you're just carrying this extra weight, and you want to minimize your mass that you're sending. Because if you send less of this empty structure, you can send more of this important stuff. So basically what happens is you lift off, and then you get rid of this. Once the fuel's gone out of here, you just ditch the fuel tank. No longer a problem. You don't have to push that weight anymore. Now you're in the second stage. You use up this fuel, and then once that fuel's all gone, you get rid of that. Now you're just this. You have a lot less to push, because otherwise, if you didn't do that, you'd have this amount of fuel pushing all of this dead weight as well. So it makes so much sense just to get rid of the dead weight. That's why you do rocket staging. In fact, in the case of Apollo going to the moon, this was really just to get out of the lower atmosphere, and this was to get into orbit. And then this one was for translunar injection. So basically, they did one burn that sends them to the moon. Because the way everything works in space is you don't use your engine very much, actually. You have to use it full time trying to get up into orbit, because that's a really big job. We live in this enormous gravity well. Earth really pulls us down a lot. But once you get into space, things that keep going. So you do one burn for 5 minutes or something, you fire your engine, and then you're just sailing, cruising, no firing at all. So you just shut down the engine. Whereas with an ion engine, which pushes only a little bit but pushes very efficiently for a long time, you just fire it constantly. So those things fire for months. And why, you see a lot of these, the Space Shuttle had 2 of them as well. There's these solid rocket boosters. Why do you use those? Yeah, exactly. It's like a side stage. Same reason you use stages, but there's actually something else about them too. They have a lot of thrust, but they're really inefficient. What that means is what you want close to the Earth is a lot of push. You need a lot of thrust to escape gravity. But you don't really care if it's efficient, because you just want to get away as fast as possible. The sooner you get away, the sooner you have to stop pushing. So there's a real trade-off, and what you want close, you want this stage to be able to push a lot, because you want to get up as soon as possible, but you don't really care if it's that efficient. So you really want to choose this stage for high thrust, and solid rocket boosters are very high thrust, but pretty inefficient. And then you can just get rid of it, and then it's just an extra push that you got, and you can get rid of the structure. But the upper stages usually use a different propellant, use one that's more efficient, that pushes less hard, but can push for longer, because you're already in orbit. So it's much better. And so solid rocket boosters is just an extension of the staging, but it's an extreme extension where you have this really inefficient but high pushing rocket at the start. We already talked about thrust. Thrust is the amount of push you get, the amount of force you actually get. ISP is the efficiency. So something like an ion engine, which can push for a long time, but doesn't push very hard, that's really efficient. And delta V is the change in velocity from the equations. So if you go from one speed to another, you're going to keep that same speed because there's no drag, right? Things move very, 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 very fast in space. To put it in perspective, if you achieve about 7 kilometers per second, that's across the Boston area in a second, then you can get into orbit. That's how fast you have to be. So it's very, very, very fast. And that's why things do so much damage in space too. Little pieces of dust moving at 5 miles per second is a lot of energy. Here's a comparison of some current engine technology. So solid rockets, you can see, have a lot of thrust, but aren't very efficient. So exhaust velocity is a measure of efficiency, right? And then you get to something like an ion thruster at the bottom has a really, really fast exhaust velocity, but a lot less thrust. So it's a complete trade-off. You either want a lot of thrust and you don't care if it's efficient to get away from gravity wells really quickly, or you want something that can push for a long time, is very efficient, but doesn't have a lot of thrust. It depends on what you're doing. So what kind of propellant do engines use? What are the different kinds of engines, rocket engines? Pardon me? Oh yeah, well that's for car. But for rocket, there's different kinds of propellant. Well, let's talk about states of matter, I guess. Yeah, absolutely. So liquid propellant, you can have liquid propellant where you mix it. There's actually some that are three different types, but generally you have two different types of gases that you mix and then you have to ignite. And they're often stored as liquids, like liquid hydrogen, liquid oxygen are very low temperature, and the only reason why you store them as a liquid is because you can store much more of them. They compress much more. And then as soon as you mix them, you ignite them, and then you get this explosion essentially in the nozzle, or in the combustion chamber, and it blows out the back of the nozzle. And as it expands, it actually increases in velocity. Sometimes you have two types of propellant, sometimes you have three, sometimes you only have one, actually. It's called a hypergolic. If you don't need to light it, if you just have a single propellant, sometimes you just shoot one type of propellant at the back. That's less efficient, but it's much simpler. So if you want a cheap system that you're only going to use once, then sometimes you use that kind of thing. There's also a complexity factor. The shuttle, for its main engine, used liquid hydrogen, liquid oxygen, which is pretty high thrust and pretty efficient to get up. But then once it's in space doing maneuvers, it never actually fires that engine in the back again. And in fact, the space shuttle, you see, has this big engine at the back, but it can't even use it in space. What it has is these little thrusters. It's called orbital maneuvering system and reaction control system. And you see, have you ever seen those shots where you see these little poofs, and it's kind of maneuvering like that? That's what it uses in space. And it's actually just one type of propellant that it uses. It doesn't use the rocket. It doesn't mix any gases, doesn't mix anything like that. It just does little firings of its thrusters. You can also have solid rockets. And the way that works, if you look down, if you have a rocket like this, usually it's a shape. So you have a hollow section in the middle down here. And if you looked at a cross section of that, it's often shaped in funny shapes like this, maybe. And it's because you want to get even burning. So all that is you just basically light it on fire. It's like a whole bunch of gunpowder or something. It's not really gunpowder, but something much better. But basically it starts burning around the edges, and you just get this fire shooting at the back. And you want to shape it in such a way as that at each section you get an even burn. So it's always burning at the same rate. Well, not necessarily even. You want it to be a specific type of burn. So it could be different. You could shape it so that it does, like it burns faster at the start and slower later on, something like that. The problem with a solid rocket is that you can't reignite it. Once you light it, it's a firecracker, and it is just burning until it burns out. There's no way to stop it. So those solid rocket boosters, once you light it, it's gone. You can't turn it off. So that's why you can't use it in space for moving around. It's only for a very specific purpose. Whereas a liquid one, usually you can reignite it. You can turn it off and restart it, but not a solid rocket. Station keeping is just, as I said, there's some drag in orbit. So if you need a boost to stay up, you do that as well. Most satellites, even though they're just in orbit, they actually have a propulsion system to keep them in orbit because there's a little bit of drag, so they have to fire every now and then. And the space station does that as well. So here's an example of an ion engine. That's kind of what it looks like. And it's just shooting this plasma out the back really fast. But it's using an electric field, a coil, because the ions that it's shooting are electrically charged. It has this coil like this. And it's just these little electrically charged particles. And it creates a spectrum where it's like positive at one side and negative at the other side. And maybe these are positively charged, so they get sent away from the positive and sucked towards the negative. And this happens super, super, super fast. and so they just get shot out the back. It's like a rail gun. It works kind of the same way. You just have coils that make an electric field, and it shoots electrically charged particles. So it's shooting just basically atoms, but it shoots them so fast, or ions actually, which is an electrically charged atom. But it shoots them so fast that you're not using very many of them, and you're not putting a lot out. But you can keep firing it forever because you're hardly using any material at all. You're just shooting little tiny particles of gas. Yep.
Why can't you shoot more out?
Why can't you shoot more out? That's a good question, actually. Because I think, well, for one thing, you have to turn it into a gas. You have to gasify it with a reaction. I think there's a limit on that. One of the main restrictions on this is it takes a lot of electricity. So I think it's a function of how much electricity you can afford to do that, to gasify it. And I think the other thing is probably if you have a lot of particles in here, there's a certain limit to how many you can have, or you get less efficiency because they start bumping into each other and that sort of thing. So probably, I think if you're just talking about a few particles at a time, you can usually throttle them. You can make them more powerful or less powerful, but I think there's probably a big loss of efficiency because you get so many particles bouncing into each other and that sort of thing.
What would happen to someone if they stood too close, like behind them?
Oh, actually, it depends. I think that they're not actually necessarily very hot. Probably, maybe not much at all. Their thrust is so super low, it's like less than a Newton or something. You could probably not even feel it. The way they work is there's actually a space mission with them now, Dawn mission, which is going to visit Vesta, and Ceres, which are really interesting places, by the way. Ceres is a dwarf planet. It got upgraded to dwarf planet when Pluto got downgraded, so Ceres is my favorite place. And they're going to visit. It's the first mission. But it's so little, you could hardly move a piece of paper. But they fire it for months to actually go there. They fire it the whole time. To do an orbit change, if you're in space and you're in orbit and you want to go to a different orbit, you have to fire your engine, right? But and normally it's like, okay, we're going to fire our engine here, and then we're going to go into a different orbit right away. But with an ion engine, you actually fire it for months, and your orbit's like this. It's like this spiral that's just a little bit bigger, where it's totally different because it just hardly pushes a piece of paper. I think it would be fine. I think that the coils themselves might be really hot or something, but if you just stick your hand at the back, it's not going to be hot. If you did that with a rocket engine, yeah, I mean, forget it, obviously. So that's a normal rocket engine. This is an example of how a fusion engine would work, but we don't know how it works. This is this is a nuclear thermal engine, which people are developing. They were developing in the 60s, but then they sort of canceled it. It is actually very similar to a chemical rocket, but what it does is instead of mixing two gases or liquids and causing an explosion, it uses a nuclear reactor to heat them really hot and then shoot them out the back. So it's kind of like a hybrid between an electric engine and a chemical rocket, except it uses nuclear power to heat rather than an explosion, an actual combustion. Yep.
So in space, would the ion rocket go a little faster than on Earth?
Would it go faster than?
Because of the no gravity.
Oh, the amount of push that you get out of it is the same, right? But you couldn't even use it on Earth because it wouldn't push fast enough. You wouldn't even overcome drag. Like if you tried to put an ion engine on a car, it wouldn't move at all. It just wouldn't move. But in space, because there's no resistance, if you fire that thing for a month, it just builds up forever. So that's why it works. Okay, so here's Dawn. This is two different strategies to do two different missions. So the point here is, depending on what you want to do, you make different choices. It's always a trade-off. So this one is Dawn. This is the one that's going to Vesta and Ceres. Those are Ceres is the largest asteroid in the asteroid belt. You've probably heard of the asteroid belt between Mars and Jupiter. Ceres is the largest one. It's about a tenth the size of the Moon, so it's pretty big. I mean, it's the biggest asteroid by far, and it's now classified as a dwarf planet. And Vesta is one of the other four biggest. There's Pallas, Hygeia, Vesta, and Ceres are the four biggest. And together, those four make up about 80% of the mass in the entire asteroid belt. So Dawn is a spacecraft, and it was in orbit around Vesta for a few months, and now it's on its way to Ceres. And it uses an ion engine, and they were at Vesta for a few months just doing very slow spirally orbit changes like that. with its ion engine. And because it doesn't need to carry a lot of fuel, that's the advantage of an ion engine, no fuel tank. It has a fuel tank, but it's a small one. They can use this little fuel tank like this and hardly use any of it just to put